Okay, so yeah, I gave you one function that is f of x comma y, 0.1 x square plus 2y square to minimize. And many of you have used Sylvester criterion because it's a function involving two variables and checked that 0, 0 is the minimum. 0, 0 is the minimum of this objective function f of x comma y. Okay. Now you will see, we will see, I think I have written a code. We'll see that when you use gradient descent to solve this objective function, it fails. Gradient descent fails. It fails because of one particular reason, because of the shape of your function. The shape of your function is like this. Shape of the function is like this. That means it is flatter on the x-axis. It is flatter on the x-axis. Okay. And it is elongated on the x-axis because of this 0.1 term. Because of this 0.1 term. Okay. So therefore, the gradient descent fails when you have a objective function which is flat. It means that in one x direction it is like flat, and in other direction it is expanding. Okay. So therefore, in these kind of situations, when in one direction gradient is less, in another direction gradient is more, those cases, okay, gradient descent method fails. Okay, gradient descent method fails because it has to check. Gradient descent only works with the magnitude of step size, magnitude of the gradient, and direction of the gradient. Yes. So therefore, if you have a flat function like this, gradient descent fails. Okay. And this is the reason why we cannot always rely on gradient descent. Okay. Therefore, we have to develop new methods. And this motivated researchers to develop this method, momentum. Okay. We will see that gradient descent approaches very slow in this function. To give a momentum to it, we use a momentum method. Okay. So it is just a new variation of gradient descent. New variation to gradient descent. Okay. So therefore, we come to this momentum function. We will see this example a bit later in the class. So in particular, like these are the slides. In particular, you can see for noisy gradient, we need to be a bit extra cautious. Noisy gradient, which comes stochastic gradient descent, okay, or mini-batch stochastic gradient descent, which uses noise. Why it uses noise? Because it so that your algorithm doesn't stall or get stuck at a particular local minimum, okay, which is not desirable. You want some other minimum, but there are a lot of local minimum and your function is getting stuck at a particular local minimum. You need noise to kick it out from that local minimum. But apart from that, you need to be extra cautious because when it comes to choosing the learning rate in the face of noise, we will see some learning rate can make your algorithm diverge. Some learning rate can make your algorithm converge. Okay. So if you decrease the learning rate too rapidly, you will see that convergence stalls. It will go very small steps to your local minimum. If you are too lenient, that means if you increase eta to be more, you might fail to converge, okay, to a good enough solution. Fine. Because you have this noise which will be keeping you away from optimality. Okay. So fine, these are about about learning rates. And we also saw that mini-batch stochastic gradient and variance in gradient reduction. The mini-batch stochastic gradient descent updates rule on averaging the gradient over a batch, and that reduces the variance in your gradient computation. That we saw. We saw that variance in gradient in mini-batch gradient descent is inversely proportional to the batch size. Yes, BT. Okay, so if you increase your batch size, variance in the gradient decreases. Okay, so therefore, mini-batch gradient, stochastic gradient descent, you can use it to reduce the variance in gradient estimation. Okay, this is just a recap. This brings me down. To another concept, that is instead of average, you can use something better, that is known as leaky average. I hope you must have heard this term. Did in time series you heard this? Leaky. Leaky, you heard. Okay. So we will see what is leaky average. Leaky average, I will give you one example. Maybe that deserves one example now so that you don't get confused later. Yes. Leaky average, or also known as the moving average, is a technique where instead of just using the most recent data points, you can take average of recent past values to smooth out fluctuations. Okay. So you can see that suddenly, like you can see the example here. So tracking the daily temperatures. Okay. You can track the daily temperature and you have day 1, day 2, day 3, day 4. Day 1, day 2, day 3 are 30, 31, 32 degrees Celsius, but day 4 suddenly jumps to 35. But if you take the normal average, you know that mean has this uh, limitation that one particular small quantity, if is in the mean, it will bias the mean, isn't it? If one particular sample data is smallest, 0.1, then all the mean will shift to that side. Okay. If you have a very big quantity in your mean, it will shift your mean to the bigger side. That is the limitation of mean. I hope, therefore, you know why mean should not be used in much of your data analytics concepts. Okay. Like if there is a missing term, it is not that wise to use mean. Okay. Because you don't know how other data sets behave. If one of the data set is very big, then if you take the mean, then it will get biased to that bigger set, bigger value. Okay, therefore mean is not an ideal candidate, rather median is an ideal candidate in your all many of your data analytics concepts. Okay, I hope that is being covered. Okay. So instead of, if you take a mean, then the mean will get biased to 35 degree because that is the most important, right? So yeah, is it clear for many of you, or maybe can you compute the average of this? Let us see normal average. What is it? So you're getting kind of 32. You're getting kind of 32. Okay, fine. So now we will see a simple moving average or the leaky average over 3 days. Over 3 days, you want to see the moving average over 3 days. So what we do, it means that each day we take the average of the last 3 days. Okay. So day 3, if you want to see for day 3, then average over the previous values. Okay, so day 1 plus day 2 plus day 3, 30 plus 32 plus 31, divided by 3, 31 you got on day 3. Okay. Hmm? Which one? No. For day 3, if you want to compute the moving average, you have to take all the previous values which you have. You have to include this value also. Yes. If you want to compute day 4, take all the data before you. That is, oh, yeah, but you have to take 3 datas. Huh. So therefore, if it is day 4, you are taking the previous in that day. So day 4 you took, that is 1, day 3 you took, that is 2, day 2 you took, that is 3rd. So 32 plus 31 plus 35. Okay. So you're getting 32.67. So you can see that this, by considering this moving average, this is just a tiny example, but by considering this moving average, you are reducing or smoothing out sudden jumps. You are reducing and smoothing out certain jumps. Sudden jump is 35 degree. This is a sudden jump. Okay. Which might affect all your dataset computations. Okay, so therefore this is an example of leaky average. Okay, what you understood from this concept? What you understood from this example? You understood from this example that if you want to compute the temperature at day 3, you are considering the past values in your picture. The past values in your picture. Okay, you can see day 1, day 2 is also included. The same idea we will use in momentum gradient method. That means in your trials, in your number of iterations, suppose in first iteration you compute gradient, that is grad G1, then next iteration you compute grad G2, so on. Then what it suggests is when you are computing grad G2, you use the value of grad G1. When you are using grad G3, you use the value of grad G2 and also value of grad G1. Okay, when you are using grad Gn, use all the values of gradient previously. Okay, fine. That way, it will smooth out all your gradients. Okay, that is known as the momentum method. It uses memory. It uses memory of the previous gradients. Fine. This momentum method will be one of the most important method to use, and it is being used in ADAM optimizer. Okay, it is the left hand of ADAM optimizer. RMS prop is the right hand of ADAM optimizer, and the middle is the ADAM optimizer, which uses both RMS prop and momentum. Okay, fine. So we'll see. So we'll come back. So instead of this now further minimized, this further revisited the mini batch gradient descent in some way. That is, instead of computing gradient for each mini batch, which you were doing in mini batch stochastic gradient descent, I think it is clear. Okay. Instead of that, the update rule which we will use for momentum method replaces the gradient with a leaky average, defined as follows. Okay, this is the iteration rule. This is the iteration rule. Iteration rule for momentum method. Okay, so what is this method? Just by looking into this method, many things might not be clear. Many things might not be clear because it might make you understand that yeah, this is not the so yeah. So I just made a typo here. So when you are computing moving average over 3 days, okay, of day 2, if I want the moving day 2, so I need to do like 1, 2, and 3. Okay, so that means it is 30 plus 32 plus 31 divided by 3. So this I have written as 3 by mistake, so it should be 2. Okay, and similarly, when you are computing the moving average of day 3, it should be 2, 3, 4. So 32 plus 31 plus 35 by 3. Okay, so this 4 should be replaced by 3. This is just a mistake I just told. So just correct this in your notebooks. Okay, that means if you are computing the average of the second one, then all this average will be added up and taken the average over. If you are taking the average of 2, 3, 4, okay, then it is of the day 3. That means you are taking the average of all. Fine. But the idea is simple. The idea is simple that you are taking the values of the past. That is the only thing. You are taking the values of the past in leaky averages. Okay, that's the only needed concept in the gradient computation. We will take the iterates, the gradient of the past iterations. Okay, we will take the gradient of the past iterations. That is it. Nothing else. Okay. Shall we go? Okay. So I was telling you. Okay, let us be back to this. So you can see that this is the iteration procedure for momentum method. Okay, Vt equals to Vt equals to beta Vt minus 1 plus Gt plus 1. Okay, but this looks frightening. What are the so many numbers and variables? It is confusing. Okay, it is indeed confusing, but the moment you see it carefully, you will see that it is easy. It is easier thing. Okay, so what we are doing, this is the actual gradient. This is the actual gradient, Gt plus 1. This is the most actual gradient which you compute using full batch gradient descent. normal gradient descent, you just compute the gradient, that is the gradient. Okay, but we are not using gt plus 1. Okay, doesn't work in flat environments. It will not work for this function. So therefore we have to modify it. Instead of taking gt plus 1 as which is the actual gradient, we are taking a modified gradient. That modified gradient is vt. So this vt is the modified gradient or momentum gradient, you can say modified gradient. Okay, fine. How this modified gradient depends on, it uses the value of the actual gradient gt plus 1. vt uses the value of gt plus 1. Fine. But I told you we are considering leaky average. So therefore vt depends on the past value. That is, it depends on vt minus 1. And there is a constant term associated to it, is beta. So beta is kind of the decay rate. Okay, decay rate. That means how much weightage you want to give to the past gradient. The more larger beta value you choose, the more importance you are giving to the past gradient. Okay, we will see why beta alone is important. We will see why beta alone is important. Very, very nice formulation follows from this. Okay, and beta belongs to 0, 1. Okay, so this means that the updated time t includes a weighted sum of the past gradient. How many of you are able to visualize this line? Weighted sum of past gradients. Can anyone see that? See it coming? How? So Vt equals to beta Vt minus 1 plus Gt plus 1. This is the actual gradient I have taken, and I have added a past gradient here, that is Vt minus 1, and multiplied a beta in front of it. Now, what is Vt minus 1? Vt minus 1 is equal to beta Vt minus 2 plus Gt, isn't it? Is it okay? Clear? So can we use Vt minus 1 here? So what is Vt now? Beta times beta Vt minus 2 plus Gt plus 1. So what you are getting? Beta square Vt minus 2 plus beta times Gt plus 1. Can you see something occurring here? Very nice series. Okay, you can see that the gradient at t plus 1 as usual. Then the previous gradient Gt, I am multiplied with beta. I am giving respect to the past gradient. You saw that. Then I am multiplying beta square with the previous value. Now you can write Vt minus 2 in terms of Vt minus 3 and keep on going till V0, the first value. Okay. So if you do like that, can you see what series you are getting? Can you understand what series you are getting? You are getting beta, beta square, beta cube, beta fourth, like that you will get for each iteration. And what is the beta value? Where does beta lies? Beta lies in between 0, 1. So with higher powers of beta, the value decreases. Beta will be in between 0 to 1. Beta square will be in between 0 to 1, but less than beta. And beta cube will be less than beta square and beta. Okay. So you are giving higher importance to GT. Okay. Less importance to VT minus 2. Because can you see? Can you understand the logic? Can you understand the logic that Vt minus 2 contributes less to Vt than Gt? Because Vt minus 2 is multiplied by beta square, which is less than beta. Is it clear? Beta square is less than beta. So therefore, contribution by Vt minus 2 is less than Gt. How many of you understood this? Is it okay? It's just normal, like So this is what I am going to do in the next slide. Okay. So therefore, you can see why the V, that is the new gradient, that is the momentum gradient. Momentum gradient. So idea is simple. Gradient descent fails for this function. This function is not that special. It fails for anything looking flat. If your objective function is flat, cannot use gradient descent. Therefore, you have to use momentum. Okay. Therefore, you have to use momentum. Come. Okay. After that, we'll discuss. So V is the momentum gradient. So instead of the gradient gt plus 1, which is the actual gradient, you can compute, and it fails. Therefore, we are using a modified gradient, that is Vt, nothing else. Same thing, nothing else. Okay. Vt is the modified momentum gradient. So in momentum method, which one we should use, gt or Vt? In momentum gradient method, which one is the final output, Vt or gt? GT is the actual gradient, but the GT fails in this case. Therefore, you have to modify GT. That is, you modify according to this iteration rule. That is, you are multiplying the past values. These are the past value plus current value. So momentum method is you give respect to past values. That's it. Previously, so if beta equal to 0, tell me, if beta equal to 0, what you get? Yes, beta plus 1. So momentum method is equal to gradient method, nothing else. If beta equal to 0, momentum method is nothing but gradient method. So therefore, if you change beta less than 0 and less than 1, you are taking into momentum. Can you see? This is generalization. This is a generalization. Fine. So what are Vt and Gt plus 1? Exactly whatever I have told, it is written here. Gt plus 1 represents the gradient at time t step plus 1. That is the direction in which the optimization algorithm updates the modal parameters or hyperparameters. Okay, at that time steps. Okay, at that time step. Okay, fine. Gt plus 1 is just the gradient, nothing else. What is Vt? Vt is a modified version, I told you. It is a modified version of the gradient that incorporates past gradients. Okay. It acts. Why we are taking the past gradients? We saw the concept of leaky average. Leaky average was taking the past values and was able to smooth it out. So therefore, in case of this function, you will see gradient is very abrupt. We will see that gradient is very abrupt. To smooth out that abrupt variance in gradient, we are using the past values of the gradient, okay, to smooth it out. Therefore, here the concept of leaky average comes, okay, by taking the past gradients, fine. So it acts like a smoothed gradient update rather than just using the latest gradient GT plus 1. Clear? Okay, so this is already I have done it here. How they form a weighted sum of past gradients. You have this iteration rule. Now Vt minus 1 you can write as this. So you are getting this value over here. Now if you continue doing it, keep on doing it, Vt minus 2 in terms of Vt and so on, you will generate this series. I hope it is clear. Can you see? Gt plus 1, you can think of it as beta to the power 0 Gt plus 1. Isn't it? So when you take tau equal to 0, you are getting Gt plus 1. Take tau equal to 0, what you are getting? Gt plus 1. Okay, so when you take tau equal to 1, you will be getting Gt. Yes, so like that, it will generate this whole series. So you can see that how smoothly, using the simple line, we came out to this weighted average, exponentially weighted average. It is exponential because beta to the power tau, exponential leaky average. Because the coefficients are exponentially decreasing. Beta to the power tau decreases as tau increases. Is it clear? Because Beta to the power tau decreases as tau increases. Why? Because beta is in between 0 and 1. The more power of beta you take, the less you get the value. Fine? I hope it is clear. So therefore, you can see this is why Vt is the weighted sum of the past gradients. Actually, I should have written exponential weighted sum. The weight is not the simple weight, is rather something special. That is, the weight is decreasing at an exponential scale, or rather as a geometric progression. Beta to the power tau. I think it is geometric progression, right? Beta is decreasing. Okay, fine. So recent gradients Gt plus 1 have a weight of 1. So we are giving much influence to the recent gradient and less influence to the past gradients. Okay, we don't want to give full control to the we don't want to give full control to the past gradients. Yes, exactly. So therefore, how we can reduce it? We can reduce it by taking older gradients. That is, we can reduce it by having exponentially smaller weights. That is beta to the power 1, beta to the power 2, beta to the power 3, so on. Beta to the power 3 greater than beta to the power 2. How many say yes? Beta to the power 3 greater than beta to the power 2. Is it correct? Beta to the power 3 greater than beta to the power 2. Why? Milan. Yeah. Huh? Correct. It's correct, right? Why? Small value. Small means how much small? In between 0 and 1. Yeah. So, yeah, Mr. Srihari. Srihari. Beta to the power 8 greater than beta to the power 6. Is it correct? Yeah. Why? You will understand. Back, last, middle. Yeah. Beta to the power 9 greater than beta to the power 7. Beta in between 0 and 1. Is it correct? Why? Because take an example 0.1 to the power 9 and 0.1 to the power 7. 0.1 to the power 9 will be smaller. So therefore, and we are giving as tau increases, we are going to past gradients. So we are giving less weightage to the past gradients. That's it. Nothing else. Understood, right? So what you understood from this? Weightage 1, weightage 1 is given to GT plus 1, and then exponentially smaller weights are given to past gradients. Is it clear? I hope it is clear. So this is so the further back in time, the further we are back in time, the smaller the weight due to exponentiation of beta. Okay. So therefore, beta is known as the decay rate or the exponential factor. Okay. Fine. So why is it called a moving average? The moving average is a technique where each new value is averaged with the previous values to smooth out the fluctuations. Exactly what we have done here. Okay. So therefore here Vt is known as the exponentially weighted moving average because it gives exponentially decreasing importance to older gradients. It gives exponentially decreasing importance to the older gradients. Okay. So due to this, the gradient has smoothed out. This smooths the gradient updates, preventing sudden changes and helping optimization to move in a stable direction. Okay. Due to this last line, we are doing all these things. Due to only last line, the normal gradient was not able to do this in this function. Therefore, we did all of this. Okay. Hope it is clear. And then, yeah, we discussed the moving average, all the things. Fine. This we already discussed. So the same thing again, I'm repeating, but just in a different manner. How does this apply to gradients? Instead of directly using the gradient, that is current gradient for optimization, we compute a moving average of past gradients. That is, this is the iteration rule we already see. We just don't use the current gradient, but also remember past gradients. Okay, fine. Older gradients are multiplied by beta again and again, reducing their influence over time. We are reducing their influence. But remember, it's not like we are not considering their influence. We are giving low priority, but we are giving some priority, okay, to the past gradients. That's the idea. So therefore, we saw that we are getting this. So technically, momentum method is this. Technically, this is the momentum method, nothing else. This is the momentum method, nothing else. So all the previous gradient, or collect all the gradients, give highest priority to the first gradient, most recent gradient, and exponentially less gradient weightage to the past gradients. Okay. So this series you can write and say it is a momentum method. Okay. This is the momentum method, nothing else. Previously, so if beta equal to 0, what happens? Beta equals to Dt plus 1, which is nothing but the original gradient. So original gradient and your momentum method is nothing but gradient descent. Fine. So if gradients are noisy or fluctuate a lot, a moving average can smooth out. Fine. So instead of taking sharp turns or steepest descent, it follows more stable directions. This is why momentum-based optimization, that is stochastic gradient descent with momentum, works better than plain gradient descent. Fine. So therefore, you now know what is momentum. Okay, momentum, I think it is basically, it came from the statistics moment. Okay, I suggest everyone to go back and see what moment means in statistics. What is the first moment? What is the second moment? What is third moment, and so on. Okay. You will see again series like this. When you're discussing moment in statistics, I think you might be knowing better. So, so you will get something like this series. They're closed, fully closed. The smell are coming. Can you full close? Okay, so why, yeah, these are all, yeah, you know all this. This is all fine, like, so yes, effects of beta, yes, effect of beta. So a large beta will result in long range average, accumulating more historical gradient information. That means, if you increase your beta value, you are giving reference to the past or historical gradients. Okay. A small beta will result in slight modification to the regular gradient method. But if you increase the beta, it will give a good momentum, more to in addition to the original gradient. Okay. This prevents gradient updates from following the steepest descent of current step too aggressively, instead of smoothing it out the update direction. Okay. Fine. See, these are all the slides are like saying you the same thing in a kind of a different way and a different language, so that you get motivated a bit. Fine. So, fine. So, I think this you already know. Yes, this is the most important thing. this is an ill-conditioned problem. This problem I gave you on the board is an ill-conditioned problem. That is why gradient method was not working. And that's why exactly if you have an ill-conditioned problem, you can use momentum to it so that it will work. Momentum to stochastic gradient. Okay. So therefore, momentum methods help in poorly conditioned problems where progress is slow in some direction and rapid in others. I hope I can give you one small example. Someone is riding the bike. Okay. Someone is riding that bike. Suppose it's that bike. Okay. So someone is riding that bike, and you have like you are going it on a good day, sunny day you are going, but it rains. What you do? If it rains, you wear one rain jacket. You wear one rain jacket. So on a sunny day, what weight did you give to the rain jacket? Zero. On a sunny day, you gave zero weightage to the rain jacket. You did not wear it. Did you wear on that sunny day? No. Did you wear? No. So therefore, but it rains, you wear. Yes, that means if it rains, you are giving weightage 1 to the rain jacket. That's the exact same thing. Okay. So it helps like you can see it doesn't change the way you ride your bike. Okay. It will just change a bit. That means just a bit is like using the rain jacket. But it did not change the original one. Did it change? No. So okay. So anyway, this approach was studied in deep learning and optimization processes. Okay. So this momentum method is useful in deep learning. Why? Because Adam optimizer is the uses momentum method as its right hand. We'll see. So it was originally proposed by Pollack. No need to know, but just a motivation. Nesterov, who developed this Nesterov accelerated gradient or NAG method. So a widely used optimization technique in your deep learning programs. So this momentum based method is inspired from leaky average. Actually, leaky average is the only concept due to which momentum method was created, and it improves the convergence speed and stability in your deep learning optimization problems. By using past gradient, they reduce the noise and avoid sudden updates or erratic updates, okay, making the training to be more smoother and more efficient. Right? Now coming to our problem. This is the ill-conditioned problem which I had written on the board. Okay. This is a quadratic function which has an ellipsoidal shape, which you saw already in Desmos. It is similar to the earlier function. I think we solved this function previously. I hope you remember it, isn't it? We solved this optimization problem for stochastic gradient descent, and many other cases. So you can see, but it is now stretched along the x1 axis by scaling x1 with a smaller coefficient. If you add the smaller coefficient 0.1 to the x1 axis, it is stretched. Yeah, okay. So I hope now you can recollect that the function has a minimum at 0, 0 because you solved using Sylvester criterion and you actually checked that the determinant of the Hessian was coming to be greater than 0 and the first double derivative of the first element was greater than 0. Okay. And at 0, 0, it was doing that. So therefore 0, 0 is the minimum. Okay, fine. So therefore you can understand this idea. Now you can, seeing the function using Desmos, you can see that it is very flat in the x1 direction because you have multiplied 0.1. Now I urge everyone that you multiply instead of 0.1, multiply 2. Then it won't be flat on the x-axis. It won't be flat on the x-axis. Rather, it will be the same as in the y-axis. It will be like a circle. Yes, 2x1 square plus 2x2 square. It is just like x square plus y square equal to some constant. That is just like having the center of the circle at 0, 0. This is sudden fluctuation. Leaky average. Yes. So this is the idea. So therefore, this due to this 0.1 coefficient only, it makes the problem ill-conditioned. Okay. Meaning that gradient descent can be slow and inefficient due to vastly different scales in different directions. This is exactly the reason why gradient method was failing. Why gradient method was failing? Because On this direction, it was very flat, it was extending, but on the y-axis it is very narrow. So in different direction, if you compute, the gradient will be different. If gradients are different, the way of saying it is gradient is at different scales in different direction. So therefore gradient is confused where to go to minimize. Okay, therefore gradient descent fails, and you add a chunk that is momentum to it so that it works. So we'll see. Yeah. So why this is important? Because gradient descent, large differences in curvature, that is steep along x2 and flat along x1. So you can see, you can remember that it is flat along x1, right? Many of you have seen that. It is flat along x1 and steep along x2. This causes the optimization to zigzag, like it will be like this. It will do like this. Gradient descent will do like this. Here, then again come here, again come here. All this. You will see that in gradient descent. Instead of just smoothly converging, it could have converged smoothly like this. You've seen gradient descent doing both of these, A and B. I hope seen. When we took a parabola, I think you have seen it was zigzagging to the optimization. It could have come smoothly to that. So did not happen. So therefore, a high learning rate can cause instability and low learning rate can make the progress slow, that you already know. This is where momentum-based method help you by accumulating the past gradients. Okay, by accumulating the past gradients which we saw, which allows the updates to be more stable and faster in flat directions. Fine. So we will experiment using Python. So with the learning rate, we will use the learning rate 0.4 and observe how gradient descent behaves on this. And then we will experiment. Then we will see that gradient descent struggles. Gradient descent will struggle, okay, in this problem. Whereas we will see, okay, we'll see that in Python now. Yes. So, exactly. Okay. I think I forgot to include the momentum. I just included the normal gradient descent. Anyway, this is the normal gradient descent. You can see we are starting from 1, and then you can see we are not even converging to the 0, 0. The cross value you are seeing, this exactly same figure you got in Desmos, I think. Okay. So you can see it is flat direction, but it is steep on this direction. X1 is the x-axis, x2 is the y-axis. Okay. Now you can see that I have started from here, this point as the initial condition. What? No. Let me check the initial condition. What is the initial condition here? Yes, you can see learning rate to be 0.4. We are defining the function. This is the gradient, and this is how the learning rate is multiplied with the gradient for gradient descent method, normal gradient descent method. And we are initializing the variable. X1 is 4, x2 is 2. X1 is 4, x2 is 2. Okay. We are starting from here, then normal gradient descent, you can see even after 20 epochs or 20 iterative steps, it has not yet reached to 0, 0. Can you see it has it reached to 0, 0? No, even after 20 iterations, it has stopped here. But to be honest, your Sylvester criterion, you did that process, isn't it? You used Sylvester criterion to find that 0, 0 is the minimum just by normal computation. Whereas gradient descent, even after 20 iteration, is struggling. It has not yet given us that 0, 0 is the minimum. I have given 0, 0 to be the minimum. I have marked. But gradient descent has not yet reached 0, 0, the optimum level, even after 20 iterations. Okay. Shall we try something. I hope it works. I don't have to run all the previous ones. Oh, it ran. Okay. Can we take more iterations? How much you tell? 100. Okay. It will take a bit of time, I think. No. Wow. Huh. Yeah. But yeah, at 100 it converged. At 100 it converged. But is the 100 more or less? Maybe it can converge in 80 also. Yes. Can it converge to 60? Yes. How much you tell? 40? No. At 40, it has reached very close to 0, 0, but it has not converged to 0, 0. So at 40 iteration also, we can say gradient descent did not converge yet, which is a drawback. So therefore, I suggest, I did not show, maybe next class I can show you how using momentum we can converge much faster. Therefore, I told you, normal gradient descent converges very slowly in this 40 iteration. But when we will use momentum, you will see how many iteration it takes and how faster it can converge. So yeah, these were all the things. And yeah, here I am trying to plot different weights, effect of beta on weight decay. You can see that, yeah, I think this is fine. This is just normal plot. Like I am trying to understand how beta to the power n varies with n, which is very simple, right? Your weights, beta, beta square, beta cube, beta fourth, all this. That's fine. Anyway, so this is all the ideas. And so this is what it is. Can we take some other learning rate? You can, maybe I'll share this codes and all. You can experiment with different learning rates. 0.4 learning rate we took. Maybe you can take 0.6 or some other, and you can find that it has gone. It has gone. So yeah. So I think that is fine. Anyway, so these are all the ideas. Yeah. So problem with vanilla gradient descent. What is known as vanilla gradient descent? Can anyone tell? How many of you eat ice cream? Ice cream? All of you are eating ice cream. Jubin, no. Okay. You're old. You ate before. No, no ice cream. Gone. Last two. Okay. So, which ice cream? Now, a lot of ice cream models are there. That is mint ice cream. That is spicy ice cream. Okay. A lot of things are there. Now, I ask, what is the most common flavor of ice cream? Eh? Chocolate is the most common flavor. You first ate chocolate, therefore it is the common flavor. Yeah, so actually, yeah, yeah, which is the common flavor of ice cream? Yes. So those who ate ice cream, how many ice creams you have eaten so far? Every day one. Every day two. So morning once, lunch once, or one. So you in a year, how many? So many. So you know that vanilla is the most common. Therefore, you know better. Okay. So vanilla is the most common flavor of ice cream. Therefore, vanilla gradient descent means the most common gradient descent. Okay. Nothing else. Okay, nothing else. You don't you should not think that this is some new method we are going to learn. Vanilla gradient descent method means it's the most common gradient descent method. So you can Google it, why it is called vanilla gradient descent. But since it's the most common gradient descent, it is known as vanilla gradient descent. Okay. So anyway, you can see why the problem did not occur. Like in x1 direction, gradients are well aligned, meaning they consistently point in the same direction. Whereas in the x2 direction, gradients oscillate, change direction frequently, leading to unstable updates. This is the reason why your gradient descent won't work that much efficiently in this function. Okay, we saw the convergence was like after 40 iterations also, the convergence was not achieved. Okay, so instead of raw gradient, you see how the words are there, raw gradient. Okay, so instead of raw gradient GT, you are cooking some gradient. Hmm? What happened? Raw vegetable. You eat. No. So we use a velocity term. Instead of raw gradient, we use some velocity term that is Vt. This should motivate you why we chose the variable to be V, not some capital G or something else. V is like velocity coming from momentum, mass times velocity. Okay. So therefore, which is a moving average of the past gradients. Fine. This helps in smoothing. So now you know all the things about momentum method. Okay. So this is exactly what you do. Instead of GT plus 1, I think I will tell you whether it should be GT plus 1 or GT minus 1. I will tell you a bit later. Okay. But you know this is the momentum method. Okay. And instead of, so what was the gradient descent method for you in the last class? Xt plus 1 is equal to the past value of xt minus the step size or the learning rate eta times the gradient at that value xt. Okay. Find this normal gradient. Now what we do in momentum, we are not using this gradient because this gradient is not efficient for us. So what we do, instead we use the momentum, that is Vt. So which you can see now here. Okay, this is exactly the momentum method. Okay, instead of gradient, we are using the smoothed version of gradient. Smoothed momentum version of gradient. I hope that is clear. Hmm? Vt, you know, accumulates the past gradients. Okay, and xt updates this average gradient instead of raw gradient. Okay, fine. When special case beta equal to 0, I told you, when you put beta equal to 0, what happens? You go the same as the gradient descent method. Okay, the velocity term disappears and we recover the standard gradient descent method. Fine. This shows that momentum is an extension of normal gradient descent method rather than a replacement. Okay, so you are not replacing the method of gradient descent, rather you are extending or generalizing the gradient descent method. So momentum method you can think of as a generalization of gradient descent method. Okay, so in ill conditioned problems, your momentum can speed up your convergence as compared to gradient descent. Okay, it reduces oscillations and allows for larger learning rates without instability. Fine. So these are all the things. This you already have seen. Fine. Yes. So if you can think xt to be 1 because you are multiplying with the gradient, right? Beta 1 you multiply with the latest gradient. Beta then you multiply with the past gradient. Then beta square to the past to past. Beta cube to the older version of gradients. Yes. So if you consider the infinite limit, then it will be like a geometric progression. So don't worry about the gradient term, but rather the coefficients. The coefficients go in geometric progression, right? Beta, beta square, 1, beta, beta square, beta cube, like that. So if you see this, this is the well-known geometric progression relation, right? If you consider infinite series of geometric progression, this is GP, geometric progression, right? So if you consider it, it is the value like this, 1 by 1 minus beta. This is the infinite limit. So this kind of gives you a learning rate you can choose. For this beta, you can put the value of beta, and what value you get, you can put as a learning rate. Instead of randomly choosing learning rate, you can just use this as your learning rate. Instead of just randomly choosing anything. Previously, you were randomly choosing learning rate, right? Instead of that, you can use this value, the converged value. Okay. I think we will see this in Python actually next class. We'll see this in Python. Somehow that code is not there in the notebook where I have considered all these things, but I will show you. But anyway, so you can see now there are two parameters. Instead, in gradient descent, what parameter was there? Learning rate was the only parameter. But in this method, you have two parameters, learning rate and beta. Okay, learning rate and beta, two parameters. So depending on this, you are actually getting the momentum based gradient descent method ongoing. Okay. So this you have already learned the series. Yeah. So this is the RMS prop. Maybe we can cover it in the next class. Is it? So yes. So what is the plan? What is the plan for this is now you have learned momentum method. Maybe I can use it in a. So what we learned so far? So far in this course, what we have learned, we have understood optimization, like optimization in the sense that optimization, but from a that is numerical methods, in the sense that we understood how you can learn 1D optimization, that is through Newton's method. We saw that. Okay. How was Newton method working? Xn plus 1 is Xn minus, yes, this should reminiscence of the Newton's method in root finding first semester course. Okay. Instead of just that, you are adding extra derivative to it. Then we saw multidimensional Newton-Raphson, right? We saw multidimensional Newton-Raphson, isn't it? How multidimensional Newton-Raphson works? Instead of xn, you have a vector xn plus 1, that is xn minus f prime. I told you who plays the role of f prime? Gradient. Who roles the role of f double prime? Hessian, grad f. So this is the multidimensional Newton-Raphson. Okay. Then we thought that yes, there are some good methods than the Newton method, because here f double prime can be 0, which quasi-Newton methods, but we have not yet covered it. I'm not sure if we can cover in this course because we don't have that much amount of time to dedicate only on optimization. But if time permits, if suppose next semester we can have one optimization method solely towards data science, optimization method for data science. This one was optimization method more closely towards deep learning, but we can see optimization method more closely towards data science if there will be an elective course next semester. If there will be, I don't know if it will be or not. Okay. Quasi-Newton method. Then what we learned Sylvester criterion. Sylvester criterion. What Sylvester criterion tells? You update, you set grad f x equal to 0. To update grad f x equal to 0, you get x star. That are the critical points. Those are the critical points. And to know if those critical points are minima or maxima, what you do? You take the Hessian. Yeah, the grad fx or the Hessian hx. Okay. You check whether it is greater than 0 or not. If it is greater than 0 and dou 2f by dou x1 2, that is the second derivative of the first variable, greater than 0, then it will give you x star is minimum. Fine. Okay. Then what else we learned? I think after that, we learned the importance of gradient. We learned the importance of gradient, how gradient acts as a vector, and how gradient points to the direction of maximum increase. Direction always points to the direction of maximum increase of the objective function. So if you want to minimize the objective function, where you should go? Negative of the gradient. So you should go opposite to gradient direction, in order to minimize the function. And why such direction is the best direction? Why it is the unique direction? Because along that direction, there will be a steepest decrease. Okay, that will be a steepest decrease. Okay, fine. So this is how we saw the importance of gradient. We saw the example of that function which was increasing. We computed the gradient, okay, and it was pointing like this. Okay, the same direction as the normal. If you take a tangent, this one was the tangent direction. The green direction was the tangent direction at that point, and the red direction was the normal direction and also the gradient direction. So if you wanted where the minimum is, the minimum was somewhere here. And if you want to find the minimum, you had to go opposite to the gradient. Okay, I hope that was clear. Fine. Then what we did, then actually I forgot, but we discussed a lot of good examples of like how to optimize when you have a non-differentiable function. When you have a non-differentiable function, that is, we took one mod function and we saw that you have, instead of derivative, in this example, you cannot set derivative to be 0, which you always do. So what you have to do, you have to include subdifferential. You have to include subdifferential and subgradient. Yes, subdifferential and subgradient concepts. Okay. To understand what we saw, if this function has a minimum, if this mod function has a minimum, then what should happen? You have to define multiple ways. Otherwise, there is also a theorem which I covered in class. What was that? Yes, exactly. 0 belongs to the subdifferential. If 0 belongs to the subdifferential, then that function can be minimized. Okay, fine. Then we also covered normal and tangent cones. Okay. In this part of the course, I think it got a bit more mathematical, like in the sense that you had to visualize. There were a lot of notations, but you know why we did that. Okay. So through this, you come to know how to differentiate, how to optimize non-differentiable function also. These functions are differentiable, but what you will do when you encounter non-differentiable function? Okay. Then we saw what are convex sets and convex functions. We also saw these things. Okay, when you can say it is a convex function, take the function. If you have the chord, if you have the secant, like yes, above that function blue, red is above blue, then it is a convex function. Okay, that we wrote with some conditions. Okay, we saw some examples of convex functions. We saw why convex functions are more important in optimization, because they usually have a local minimum. Okay, but what happens if you take non-convex functions? We took some Python examples of like x cos x. We took some example like x cos x. Okay, so in that function we saw there were multiple local minimums. Each of them were a local minimum. Okay, in that case, how your method can fail? Okay, so therefore convex functions are a class of functions where you can actually apply a lot of optimization algorithms, and therefore non-convex functions, applying optimization algorithm to non-convex function is a bit tricky. Okay, so therefore they have made a class where all the algorithms and all the methods can actually work. Okay, then we came to something more important, that is we came to gradient descent. Okay, we came to gradient descent method, we came to gradient descent method, and we saw that in Newton-Raphson, we actually saw a visualization of Newton-Raphson method in 1D. That is, I told you that if you start from there and optimization is here, that you have to tell which direction the function has to go and by how much amount it has to go. That exactly gets captured in gradient descent. So that is xn plus 1 is xn minus the learning rate or the step size times the gradient of f at xn. Okay. So this was gradient descent. Then what we did, we saw that gradient descent can be even, because this is an order n operation, and it can be made more faster by taking stochastic gradient descent. Stochastic gradient descent. That is xn plus 1 is equal to xn minus eta times grad fi. Okay. Fi, you can see there are n training samples, I drawn randomly. Okay, I drawn randomly. Fine. So this includes the stochasticity nature in this, and we saw that it can be even optimized because it is order 1. It can be even optimized using mini batch stochastic gradient descent, where you divide the same thing. It works as same as the gradient descent method, but here what you do, you divide by the batch size and take the summation of gradients. Okay, take the summation of gradients. Fine. So yeah. So we saw why mini batch gradient stochastic gradient descent works faster than all of the above, gradient descent and stochastic gradient descent, because only one thing, because of the GPU. There we saw some GPU advantages, that you can vectorize and parallelize each of the jobs or batches into each job to each GPU or CPU. Each batch you can give it to each CPU to work it out, and in the same time you can get the mini batch stochastic gradient descent. Fine. So that we read, and we also read where gradient descent can fail. Gradient descent can fail in condition systems. That is when you have a objective function in which gradient has different scales in different directions. In this example on the back, we saw an ill condition problem where gradient this side was bit slower and gradient on other side was bit faster. Okay. So in those kind of situations, when you have multiple scales in the problem, you have to use momentum. You have to add momentum with stochastic gradient descent. That was momentum based stochastic gradient descent. Okay. Now in the next class, we will start with RMS prop, that is root mean square propagation. Okay, root mean square propagation. It uses the same idea. That means we will give respect and we will include and give weights to the past gradients, exponentially decaying weights to the past gradients. But we will see why we are calling it the root mean square. So here we will see why we are calling it root mean square, because we are taking a square root. We are taking a square root of ST. Okay, ST is another way of approaching gradient, and we are taking, instead of the gradient GT, we are taking the square of the gradient. And ST actually approaches the square of gradient. Instead of taking square of gradient, we take the exponential average, and we take the square root of the square gradients, sum of the square gradients. So therefore, it's a root mean squared average. Okay. So therefore, you will see that it actually works better. Now, what is coming ahead? So the idea is simple. You know momentum, and we will know RMS prop, and all the above gradient descent methods, all gradient descent methods. If you combine, it will be Adam optimizer. Okay. So that we will cover after RMS prop, because momentum and RMS prop are actually necessary to understand Adam. Adam optimizer you cannot just learn by ignoring these. Okay. So therefore, you know why we covered Adam optimizer at the last. Okay. That will be Adam optimizer, and if time permits, we can cover the scheduling, the learning rate scheduling a bit, if permits. If it is too hard, we can skip it. Okay, I'll just tell a bit theory about it, and that will be the end of the optimization module in this course. Then we will start with regression, like multiple regression. Was multiple regression covered? like y is a function of x1 and x2, all the things. Yes. So did you use pseudo inverse? Pseudo inverse? No. Okay. Okay. So maybe we will. I urge you, everyone, try to understand this command or this function in Python. PINV. What is PINV in Python? Randomly, I will ask someone in next class. I'll write it. Okay. I will ask randomly in next class. So PINV command in Python, what it does? Okay. Why is it useful? So we will go to regression. We will learn how a multilayer perceptron is being used. We will see a bit of basic of neural network and how neural network can be used for regression. How actually basic regression, that is y equal to beta naught plus beta 1x, linear regression, simple linear regression, you can think of as a neural network. Okay. So we will see regression, we will do some problems, and that will be the end of regression. And then different methods we will learn. That will be the end of the course. Okay. So this is the outline I have so far in my mind for this. Okay. I am doing actually, to be honest, I am doing actually the momentum method. I gave weightage 1 to optimization, a bit lower weightage to regression, and then small weights to other topics as far as we go through the course. Okay. So that's the aim. So yeah, with that we can wrap it up now. Okay. And instead of that, we can hear from you guys regarding the capstone. Okay. So yeah, anyone?